Yes, thank you, Rodolphe. Good morning, everybody. So my name is Benjamin Rotenberg, and today you will see me for 2 lectures in the morning and for the practical session this afternoon. This first lecture will be about mesoscopic hydrodynamics. The second one will be about more specific simulation techniques for mesoscopic hydrodynamic simulations called lattice-Boltzmann. And before we start the first one, can anyone tell me what mesoscopic and hydrodynamic mean? So mesoscopic has to do with the scale we're looking at, just as Rodolphe mentioned. And mesoscopic would be somewhere... Yeah, exactly, somewhere between microscopic and macroscopic. So that means larger than molecules, but smaller than the macroscopic world we're used to. And on these intermediate scales, you have some interesting physics going on that require specific simulation tools that I'm going to describe in the following. And hydrodynamics refers simply to describing flows, so fluid matter, gases, liquids, and how they flow. So that's somehow different from many of what many of you are used to, that is solid materials. So I'll start with what you are familiar with, namely continuum hydrodynamics. How do we describe flow on a macroscopic scale? And I want to spend some time doing this because that will allow me to remind you the basics of the fundamentals of hydrodynamics. And also, it will force you to think about the importance of various contributions to flow. And that will be something very important when you think about how to set up a simulation for mesoscopic simulations. What are the relative importance of different aspects? Then I will go down in scale and consider really the mesoscopic scale and focus on the effect of the solvent, the various effects of the solvent on suspended particles in the fluid. And in particular, I will discuss what are called hydrodynamic interactions between solutes. And finally, I will move on to simulation techniques on various scales. And that will give me an opportunity to introduce you to mesoscopic techniques, but then that will set the stage for the second lecture, which will focus only on lattice-Boltzmann. So I'll start with the larger scales where hydrodynamic simulations are very common. And that's the global scale of the Earth, where you can use hydrodynamic simulation techniques, for example, to predict the weather on a day-to-day basis, but also when you have specific events, like for example, here is a plot of the wind velocity in the Hurricane Katrina a few years ago. And if you want to predict the trajectories and the impact that the hurricane will have, it's very useful to do this kind of hydrodynamic simulations. On the right side, you have another global simulation that does not focus really on the wind, so the motion of air itself, but rather on the fate of the radioactive plume that was released after the Fukushima accident in Japan. So what you will see in color here is the concentration in cesium in the atmosphere in the next days following the accident. And the simulation was done in order to predict what would become of the radioactive matter that was released during the accident. And of course, if you want to do this, you need to be able to predict what the wind will look like and how it will transport matter on a very global scale. Now, on a more human scale, you can use hydrodynamic simulations to predict flow patterns around more familiar objects. So for example, in aeronautics, you want to design planes in order to minimize drag and to also optimize the flow profile around the wings and the whole aircraft. Here is another example. So you see here a propeller in the middle, and the simulation shows one component of the velocity field in time as the propeller rotates. And for example, if you're designing a boat, it's very important to know what the flow around the propeller will look like, because if the velocity is too high, then the pressure will drop below zero. You can have negative pressure. You will nucleate bubbles in water. That's called cavitation. And then when the bubble collapses, it will generate shock waves that may damage the propeller itself. So that's very important also in this context to have a good description of the flow around your object you're interested in. And finally, below, you have the flow around the car. That was computed using lattice-Boltzmann simulations, very large-scale simulations. And what you see here on the right side is friction coefficient as a function of the position along the black line here. And you compare the lattice-Boltzmann predictions to the experimental results, and you see that you can have a very good agreement for this property, even though it's a very complex shape and a very complex flow pattern. And even though it seems very applied, this type of simulation, it can make it to very fancy journals, scientific journals. So going again through various illustrations, you can look at the wind in civil engineering applications. You can look at energy transfer, so not just mass transport, but looking at how liquids with a different temperature will mix. So what you see here in color is the temperature as a function of position in the mixer. And moving even further down in scale, you can have now applications in chemical engineering looking at chromatographic columns. So this is a very idealized chromatographic column where you have obstacles in a channel, for example, a microfluidic channel, and you can, for example, try to predict how solutes will be transported through this chromatographic column. So these are particles, so the color indicates the concentration in particles as they progress through the column. And you see that due to the obstacles, you will have flow patterns for the fluid that will have an impact on how the solutes are transported and also how they are dispersed by the chromatographic column. So if you can use this type of simulations to make some predictions for transport through porous materials. And this afternoon you will do some simulations, so without the solutes, but to compute flow patterns in porous materials, just as this one. Finally, another couple of illustrations, but down to the mesoscopic scale now, where the objects start to be still smaller from the smaller, much larger than solvent molecules, but small compared to the previous applications. And on the top part, you have blood vessels. So what you see here are red blood cells in a capillary that mimics a blood vessel. And again, you can look at the flow of these red blood cells in the capillary. Or you can look at, this is a colloidal suspension. So colloids are objects in the hundreds of nanometers to micrometer range. So they are large compared to solvent molecules, but they are small enough to feel the effect of thermal fluctuations. And what is done in this simulation is to shear the suspension. So the top part goes in one direction, the bottom part goes in another one. So you're shearing your sample. And this will induce some collective effects in the suspension. And in particular, you will have some effects that are related to the transport of solvent between the particles. So this is illustrated here with the blue particles that are organizing in lines here to illustrate the flow pattern between the particles that will also have an impact on how these particles interact with each other that are called hydrodynamic interactions, and I'm going to come back to that later on. Are you still with me? Yeah. So what do we need to describe this type of hydrodynamic behavior? So you know that matter is made of nuclei and electrons. This is represented here. They make molecules. Every type of molecule will behave differently on a molecular scale and also on a collective macroscopic scale. But there are also some very generic features that are independent of the specific nature of the molecules you're looking at. So if you're looking at water or honey, both are very different liquids, but they will flow in a similar way. And if you're looking on very large scales and on long times, that is, say, seconds and centimeters, then they will be described by the same kind of generic laws that are conservation laws. I'll come back to that in a second. And these conservation laws involve physical properties that are specific of your material. So typically, what would be the difference between water and honey? What property would be very different in the two cases? The viscosity, of course. So in order to be more specific, how do we describe a fluid on a macroscopic scale? So starting from your discrete description with individual molecules, you want to look at a property of the properties of your fluid at a given position. And in order to define these properties, you can imagine that you have a small observation volume around that position, small compared to the flow patterns you're looking at, but still large compared to the size of the molecules, and also to what is called the mean free path, that is the time, the typical length a particle will travel before it encounters another molecule and it interacts with it. So you will have lots of collisions between particles, and the mean free path tells you how much you will travel before you collide with another particle. And this is important because that will allow you to define local averages around that given position R. And there are a number of averages you can make looking at different properties. And generally, they depend on both the position R and the time. And these hydrodynamic fields, as they are called, are very familiar to most of you. That is, first of all, the density, so how many particles you have in this probe volume, so how many particles per unit volume, or the mass density, which is what is the total mass per unit volume. Then, so this is a scalar quantity. Then you have the velocity, the local velocity, or the local flux, which is simply the density times the velocity. And this is a vector field. Then you have another type of property that you can define in your probe volume, which is the stress tensor. So it's not a vector anymore, it's a tensor. And this tensor has an isotropic component that is called the pressure. So again, you can define all these quantities as microscopic averages, or more exactly, averages over microscopic observables. And finally, you can also define quantities that are related to the energy inside that probe volume, and the most familiar one is the temperature. You can also have energy fluxes and so on. But essentially, I'm going to focus on these first examples of hydrodynamic fields because they are the most important and also the easiest to deal with. So what kind of conservation laws can we write for these hydrodynamic fields? Obviously, the first one is mass conservation. That's very generic. So you can look at the total mass inside your probe volume and look at the variations of this mass as a function of time. So how much mass you will find in the volume will be determined by how much mass enters or exits from the probe volume through the interface. And you can write that for an arbitrary volume element, and you end up with this type of relation that involves the divergence of the mass flux field. You can do the same thing with momentum, and so the variation of the total momentum inside your probe volume will be related to the divergence of the stress tensor here. And you can write yet another one for energy conservation. I'm not going to write it down because it's more complicated. And this will be rewritten in the next slide in a very familiar equation for hydrodynamics. So what do you know about momentum conservation in hydrodynamics? What is the key equation for describing hydrodynamics on a macroscopic scale? Navier-Stokes. So where does Navier-Stokes come from? You need to have an expression for the divergence of the stress tensor. And the stress tensor has different components to it. And in a more general way, you can write the stress tensor. So these are the components of the stress tensor. So alpha and beta would be x, y, or z. You have a first component that comes from momentum advection. So this could be the advection of the alpha component of the flux in the direction of, in the beta direction. Then you have a second component that is only on the diagonal of your stress tensor, that is the isotropic pressure. And finally, you have some stresses that arise from interactions within your material, and that is this sigma term here. And it has a negative component, a negative sign because it's a convention, but that's related to how you define your stress acting on your probe volume. So you have either something that exerts a pressure on the exterior, or something that tends to keep the fluid with itself. And this stress here can be written under some conditions, some approximation, as a viscous stress. And if you do the math for the divergence, you will end up with the Navier-Stokes equation. So you have a term here that corresponds to the change in the velocity at a given position. Then something that describes a change in velocity because particles that were somewhere have moved, and as they have moved, they have transported momentum. And you still have the pressure here that gives a pressure gradient term. And the viscous stresses here end up with a viscosity. So that's a simplified form of the Navier-Stokes equation. You simply have a bulk viscosity here with a Laplacian of the velocity vector. And I've also added here a volumic force, that is the force per unit volume corresponding to external forces. For example, if you have a gravity field or an electric field or whatever. So this is what describes the motion of essentially any fluid on a macroscopic scale, and it involves some material parameters such as the viscosity or the mass density of the fluid. But you can see here that you will have a competition between the different terms, and in particular this viscous term will compete with the momentum advection term. And the ratio between the two will be controlled in particular by the ratio between the bulk viscosity and so the dynamic viscosity and the mass density. And this ratio is called the kinematic viscosity. And if you look at the units for this kinematic viscosity nu, it's square meter per second. So that's the same units as the diffusion coefficient. And that's why it's also called momentum diffusion coefficient because this corresponds to how fast momentum is transported by diffusion. You can also have different ways of propagating momentum. For example, sound is another way of propagating momentum. But this corresponds to diffusing momentum. And if you look at the numbers here, you have, for example, for water, something in the range of 10 to the minus 6. That is smaller than the kinematic viscosity for air. But you know that air is less viscous than water. So the difference between the two here corresponds to the fact that the mass density is much higher for water than for air. And glycerol is something rather oily. It's more viscous, so it has about the same mass density than water, but it's much more viscous, so it has a much larger kinematic viscosity. Another comment you can make on the Navier-Stokes equation is that if you have pressure gradients, you may also have, or if you have flow, you may also have differences in the local density of your fluid. Because if you have a velocity field, then you may have also differences in the mass density, local mass density, and you can estimate from the competition between different terms how much the density will change when you have a flow. And you can make this type of estimate using the ideal gas equation of state. So for an ideal gas equation of state, the pressure is the number density times kBt. So in terms of the mass density, it's mass density times kBt divided by m. And the reason I introduce this kBt divided by m is that this is a square of a velocity, and it's called the thermal velocity. And it turns out that the thermal velocity, as I will use later on for Lattice-Boltzmann, the thermal velocity is more or less the speed of sound in an ideal gas. And if we now look at the density variation, so that's the relative change in density. For an ideal gas, it will be directly related to the relative change in pressure along your flow. And this, using the equation of state for the ideal gas, so the bottom part here is simply mass density times the speed of sound square. And coming back to the expression for the stress tensor, you see that you have a pressure term here that should be balanced by this momentum advection term. So if you look in one direction, you would have P of the order of rho m times the square of the velocity. So coming back to this ratio between pressure change and pressure, you end up with a ratio between the velocity squared and the speed of sound squared. So that's the square of the Mach number. So you're probably familiar with the Mach number. It's the velocity of your fluid divided by the speed of sound. And essentially, what this result means is that if you have a very small Mach number, so Mach number much smaller than 1, then the density variations will be small. And you can treat, so that means that it's almost an incompressible fluid. And that's again something I'm going to use later on for the Lattice-Boltzmann simulations. So the Navier-Stokes equation is very general. The mass conservation is also very general. Once you have a given material, you can solve it for essentially any flow. But the problem is that you need to specify more information about your flow. And in particular, the solution of the Navier-Stokes equation are determined by the boundary conditions. So if you have walls, or if you have obstacles, or if you have moving objects, you need to specify how the fluid behaves at the interface with this solid wall. And the more general condition, the more standard condition, not the more general, the most standard condition is to use the stick boundary conditions. That is to assume that the velocity of the fluid at the interface is exactly the same as the velocity of the wall at the interface. So if you have a fixed wall, then the velocity of the fluid would be equal to 0. And what I've represented here is the most simple type of flow you can think of. That's the so-called Poiseuille flow. You have two infinite parallel walls, and you apply bulk pressure gradient, a uniform and constant pressure gradient. And the solution to that problem, as you will find later today, but you are probably already familiar with the solution. The solution to that problem is a parabolic flow profile with 0 velocities at the wall and with a maximum velocity in the center. And this is the first flow you will simulate this afternoon in the practical session, because it already contains a lot of physical insights, and it will allow you to get familiar with the lattice Boltzmann technique. Now, this is, of course, a simplified picture of what happens at the interface. And because you have different interactions between the molecules in your fluid and the wall, you may have different behaviors at the interface. And in particular, if you have water on a hydrophobic surface, then the water molecules will not stick to the surface, but rather slide if you have a flow. And then the velocity, the average local velocity for your water molecules on this hydrophobic surface is not 0. And because it's not 0, you need to find a way to quantify how much slip you have at the interface. And the velocity at the boundary is, of course, not sufficient to define something specific for the wall fluid interface, because if you push harder, you will have a larger velocity. So a proper quantity that can be defined that does not depend on the flow regime, but rather on the interface itself, is called the slip length. So this B here is called the slip length, and it's defined. So the inverse of the slip length is defined from the ratio between the change in velocity in the direction perpendicular to the interface, the ratio between this derivative and the velocity at the wall. So looking at the slope and the value at the wall, you can define a slip length. And this here, do you know what this is? To illustrate slip at a solid-liquid interface. How does it look like? It's a swimming suit. And a few years ago, in competitions, some very famous swimmers started using this type of swimming suits that allowed to go much faster without additional effort. And short after, it was banned from competitions because it provides an undue advantage to people that have this type of swimming suit. So you can reduce the friction and modify completely the flow around you if you use a material that have a different type of interactions with the fluid you're interacting with. So far, so good? Okay. So the final point I wanted to make about macroscopic hydrodynamics is discussing hydrodynamic regimes. And so I've discussed the very generic Navier-Stokes equation and mass conservation, then something related to boundary conditions, and finally there is something that is in fact very generic, and it's not only what is on this slide that falls into the generic term of hydrodynamic regimes, but is discussing for a given flow, including how fast it goes and what are the typical size of the objects and what type of objects are suspended in the fluid, what type of other processes can occur. Depending on the relative magnitude of all these aspects, you can define different regimes based on the competition between different aspects of your flow. And one very important aspect is the relative contribution of these two terms in the Navier-Stokes equation. So coming back to the Navier-Stokes equation, you have this viscous term here and the momentum advection there. And we want to know which one dominates for a given flow under given conditions. So we simply look at the ratio between these two. And the ratio between momentum convection and momentum diffusion is called the Reynolds number. And if you introduce characteristic numbers for the velocity, u0, the size of the domain over which your fluid evolves, so that's L0 here. And then you have this ratio between viscosity and mass density, that is the kinematic viscosity. So the U dot nabla, so this is the U dot gradient of U is U0 squared divided by L0. This Laplacian here is U0 divided by L0 squared. And so the ratio between the two is U0 L0 divided by the kinematic viscosity nu. And this number here, dimensionless number, tells you whether convection or diffusion dominates in the Navier-Stokes equation. So if you have a very small Reynolds number, it means that the bottom part dominates, so it's dominated by viscosity. And if you have a Reynolds number much larger than 1, it's dominated by convection, and you will have flow patterns that look very differently, as you will see in the next slide. So another type of dimensionless number you can design is called the Schmidt number, and it tells you about the competition between momentum diffusion and mass diffusion. In a gas, for example, momentum diffusion will occur because you have particles that move and then after some time collide with another particle and they exchange momentum, and then they will go in different directions and will find other particles and collide and again transfer momentum. So momentum can be transported only through these rare collisions, and they occur essentially at the same rate as mass diffusion. So this Schmidt number will be of the order of 1. Whereas in a liquid, you are a particle surrounded by other particles. So if you start moving in one direction, you collide immediately with the next, that will immediately collide with the next, and so on. So this momentum transfer will occur much faster than mass diffusion, because mass diffusion you will have first rattling, you will first rattle in the cage of your neighbors and then escape that cage to move a little bit further and so on. So that takes much more time. And so this momentum diffusion is much larger than mass diffusion, and the Schmidt number, for example, in water will be of the order of 1,000. And again, this is a dimensionless number that tells you about different ways of transporting momentum, mass, in a liquid. Another type of dimensionless number, and that's the last one I'm going to describe in detail, is when you have a solute. So imagine a colloidal particle with a given radius r that is transported by a flowing solvent. Then it will move because it's transported by the fluid, but it will also move due to thermal fluctuations. And if you look at how fast it moves due to advection over its own size, and you compare that to how fast it moves due to diffusion over its own size, you will find this dimensionless quantity. And the Peclet number, that's the Peclet number, and that's also very useful if you want to characterize the transport regimes for your solute. And I've listed a few more, but there are many more. For example, the Knudsen number is important where you have a mean free path that is comparable to the size of your molecules. The Mach number I've mentioned previously is important to know whether you're going faster than the speed of sound in your material. If you have surface tension effects, so that's for binary mixtures, or if you have a liquid in a porous medium that is empty or that is filled by air, then you will have surface tension, and you can also look at capillary effects, so how important these surface tension effects are compared to the other transport mechanisms, and so on. So these are for chemistry, for example, if you have chemical reactions. So coming back to the Reynolds number, if you have a very small Reynolds number, you will have a flow that is dominated by viscous effects. And what you see here are experiments for flow patterns around a cylinder. So you see here from the side a cylinder, and you have a flow going from left to right. And the flow is visible here because you have a dye inside your liquid. And for very small Reynolds number, you have something that is called the laminar flow with layers of fluid that are that do not mix, essentially, and that simply go around the obstacle. Increasing the Reynolds number, you start forming different patterns at the rear parts of the flow. So behind your object, you see these circulations of your fluid. And then if you increase further the Reynolds number, you will start generating this type of regular structure, so that it's not static. In fact, they move, and you emit this type of vortices in a regular fashion. And if you go to extremely high Reynolds number, then it becomes chaotic. So you see that depending on the Reynolds number, you will have different contributions to momentum transport and mass transport. It's all described as a Navier-Stokes equation, but in the different situations here, different parts, different terms will dominate the solution of your equation. And of course, if you want to make a simulation, then you need to think about what type of regime you are considering, because you may want to use different parameters or even different techniques if you are to simulate a laminar flow or a turbulent or a chaotic flow. So last illustration of this hydrodynamic regime is an experiment where you shear a fluid in a what is called a Couette cell. So what you have here is a cylindrical cell with an axis in the middle that you can see here. And what we're going to do is to rotate the outer part of the cylinder. So the fluid is between the axis and the external wall. And if you do this at a constant angular velocity omega, then the flow inside your Couette cell, provided you are at low Reynolds number, will be laminar, and you will have a velocity that is tangential to the radial direction here. So it's perpendicular to the radial direction here, and it will be equal. The velocity of the fluid will be more or less equal to that of the wall near the wall, and then it will decrease toward the center. Because of symmetry reason, it will vanish at the center, and in between you will have streamlines that are more or less parallel locally, but of course these are circles. And you see that by doing so, you will transport mass faster at the boundaries than near the center. And you can visualize this by putting a dye inside your liquid. But if you want to see something, then you need to make sure that during your experiment, the diffusion of the dye will be slow compared to what you're doing with the advection of your fluid. So that means you want a large Schmidt number. And this is the experiment. So what you do is put a drop of dye, and you see that it doesn't move too much. So that's not like when you put a drop of ink into water, it will be diluted right away. So it's a much more viscous fluid here. And now we start turning at a constant velocity, and that shears the fluid. You see that if you have your droplet here, the part of the droplet that is towards the exterior goes faster than the other part. So you start dismantling the droplet. And if you start now, after some time, turning back in the reverse direction, then the solution of your Stokes equation will be simply the opposite field. And at some point, you will focus again your droplet. So this is called hydrodynamic reversibility. And it works because we are in a low Reynolds number regime. And it also works because we have a very high Schmidt number. Otherwise, the droplet will simply diffuse away, and we would not see anything. Okay, so do you have any questions on macroscopic hydrodynamics before we move on to smaller scales? So probably you knew at least part of what I already told. And now I'm going to consider objects suspended in the fluid that are, again, on the mesoscopic scale, so colloidal suspensions, where you have a large object compared to solvent molecules, but it's small enough that it can feel the effect of collisions with the solvent, and in particular the thermal fluctuations. So if we were to do a simulation of that type of objects, and imagine it's not just one object but many objects that may be far apart if you have a dilute colloidal suspension. But simply think about how many water molecules you would need to occupy the volume occupied by the colloidal particle. So very roughly, if they have the same density, this number of molecules would scale, so the ratio between the number of solvent molecules and the number of colloids would scale as the radius of the colloid divided by the radius of the solvent molecules to the power 3, because it's a ratio between volumes. And so if you have something that is 1,000 times larger than your solvent particle, then this ratio between the number, so you would need a number of molecules that is 1,000 to the power 3, that is 1 billion times larger. So you would need 1 billion solvent molecules to fill just one colloidal particle. So of course, that's not something you would do with atomistic simulations. And one reason you don't want to do this with molecular simulations, not only it's computationally very expensive, but also it's not necessary, because you don't care about what happens to your water molecules or your solvent molecules. You just want to know what the effect of these solvent molecules are on the suspended particles. So you want to forget about the structure of your suspending fluid and predict only what the average effect of the solvent would be. What type of effect can you think of in terms of the action of your fluid on the solid particle? imagine I have a particle moving in that quiescent fluid. If I try to push that particle, what will happen? Say I have a constant velocity in that direction. Then I will collide with molecules of solvent, so it will transfer momentum in the opposite direction. So in the end, the particle should feel some force in the direction opposite to its velocity. And this is called drag. So it's a viscous drag force or friction force. And it has a contribution that comes from the velocity of the particle and also a contribution from the velocity of the fluid. So if the velocity of the particle was equal to that of the suspending fluid, you would not feel this drag force. So it has to do with the relative motion of the particle with respect to the fluid. And there is a term here that is called the friction coefficient, which you probably already know. For a sphere with stick boundary condition, you can express this friction coefficient as a function of the viscosity of the fluid and the radius of the particle. Now I've written just minus solvent velocity here. It's a bit cheating because the flow around the particle is not uniform, but you can guess that this non-uniform flow will generate a stress at the surface of the particle, and you can integrate out this stress, and that will give you the friction on the particle. And that's actually how the Stokes friction coefficient can be estimated. So now we have a first effect, which is to dissipate energy from the particle to the fluid, and there should be an associated effect, which is getting back some energy from the fluid to the particle, and that's thermal noise. So there is a random force that comes from the thermal fluctuations of the suspending fluid, and that's called Brownian motion. And this viscous drag and Brownian motion are in fact related to each other. I'm not going to enter into details, but the very fact that your particle is influenced by Brownian motion enters in the definition of what colloidal particles are. So let's now move on with two particles or many particles. If you start moving your particle in the fluid, it will transfer momentum to the surrounding water molecules, so solvent molecules, and then momentum will go through the fluid and at some point may transfer back momentum from this particle to the fluid through another particle. So there is an interaction between the two particles that is mediated by the solvent, and it's called the hydrodynamic interaction. So the physical mechanism is what I've just said. You're transferring momentum through collisions between solvent molecules, but if you want to forget about the solvent, what you can do is simply look at the flow generated by this particle when it moves, and then look at the effect of this flow on the second particle. So that's already much simpler than keeping track of all the trajectories of all your water molecules, also all the solvent molecules. But that's still quite a lot of information because you will need to compute the flow field at any point inside your fluid. And that's something you may have to do if you have a concentrated suspension, because then the flow pattern can be very complex. You can remember the illustration in the first introduction I made. But if you want to consider the hydrodynamic interactions and forget completely about the solvent, you can make approximations and integrate out the stress that the flow generated by the first particle, so the effect of this stress on the second particle, and then you end up with an effective interaction with an expression for the hydrodynamic interaction tensor. So that's the simplest form you can imagine. That's neglecting the size, the effect of the size of your object. It's called the Ozane tensor, and it has a 1/r range, so it's very long range interactions, just as electrostatic interactions, and it also has a viscosity here. So you see that it's really arising from momentum transport through the fluid. So you may think that this hydrodynamic interaction is not important, but I'm going to show you two simulations of a sedimenting colloidal suspension. So it's initially the same thing. It's with walls on the sides and on the bottom part. And what we're doing is simply looking at sedimentation. So we have a gravity field acting on all particles. And in the left part, you will see what happens without hydrodynamic interaction. So you still have some Brownian motion, but essentially every particle feels mainly the effect of the gravity field. It feels the effect of excluded volume between particles, the effect of thermal motion that will spread the extent of the positions as you move down, and then at some point it will simply pack at the end of your test tube. Now on the right side you will have the same simulation, but now also taking into account hydrodynamic interactions with a simulation technique that is called stochastic rotation dynamics. I'll describe that briefly at the end of this lecture. And you will see that it looks very different, obviously, and you will try to think about which one seems more realistic if you've ever looked at the sedimentation of a colloidal suspension. So what you see here is that you have some laning effects. You also have some circulation that indicate the flow circulation as well. And you see that there is much more dispersion along this axis. So this is very dramatic because it's a rather non-viscous fluid. But you see that it has a very dramatic effect that is long range because the particles feel the effect of the flow as a whole and not just what happens in the vicinity. And eventually it will settle down and also pack at the end of your test tube. But you see that the dynamics is completely changed, and the flow and the dispersion of your colloidal particles is completely modified by the presence of these hydrodynamic interactions. So if you neglect them, then you have something that goes much faster, but it's probably not really representative of what the real system would behave. So let me now switch to simulations, because that was an example with simulations. What can we do to deal with hydrodynamic simulations? And that will be the rest of this first lecture, and the second lecture will focus on one particular simulation technique. And there are many challenges if you want to simulate a fluid, and in particular if you have particles suspended in a fluid. And the first thing is it has nothing to do in the first place with simulation. It's just the physics behind what you're trying to simulate covers a very wide range of lengths and time scales. So you see here that's extracted from a paper I'm going to refer to in a couple of slides. The different time scales, relevant time scales, when you're looking at a colloidal suspension. And on the longest time scale, you have colloid diffusion. the shortest events relevant for this process are collisions between fluid molecules. And you see that the shortest time scale are in the range of femtoseconds, whereas colloid diffusion is in the range of seconds. So that's 15 orders of magnitude. And if you were to do a simulation with a time step compatible with these shortest events, you would need 10 to the power 15 steps to even access the relevant timescale for colloidal diffusion. So that's not what you want to do. In the intermediate timescales, you have many other things. Like for example, after a few collisions for your solvent, you will have the decorrelation of the velocity of your fluid particles. That's this fluid decorrelation timescale. The Fokker-Planck timescale has to do with the decorrelation for the force on the particles. The sonic timescale has to do with how fast, so that's the ratio between the speed of sound and the particle radius. And then you have the Brownian and kinematic timescale. So Brownian would be the timescale associated with the friction coefficients, and the kinematic timescale related to diffusion of momentum. So that would be the radius squared of your object divided by the kinematic viscosity, whereas this one is the radius squared of your object divided by its diffusion coefficient. So in practice, you won't ever simulate that range of timescale, and you need to somewhat make some assumptions that will make the simulation feasible. And what you want is to make sure that you keep track of the relevant timescales and how separated they are. And typically, you will end up with just a few of these timescales, or even less. So here you have just the Fokker-Planck, sonic, kinematic, and colloidal diffusion timescales. And you see that we have also changed quite a lot how much they are separated. So right now, it's only a factor of 10 between each of these timescales. So it's sufficient to have them separated, but it's still rather different from the real order of magnitudes you may have in a given system. But that's a very general idea that if you want to do some simulation with a range of timescales, then you need to select just the ones that you need to keep track of everything that is needed. And you may shrink down so telescopic, they called it telescoping down. You want to have this timescale separated, but not necessarily as much as in the real system. And again, this has to do with hydrodynamic regimes in the sense that you are comparing different effects and just making sure that you are in the large or low limits of certain ratios. And whether this ratio is 1,000,000 or 1,000 is not the most important fact. The most important is that it's much larger than 1, for example. And then you have other challenges that are more specific to your simulation techniques and how it is implemented. And the first one, obviously, is computational cost. So that has to do with the timescale, but also on how heavy and how computationally expensive the level of description is. So if you're dealing with molecular simulations, you will have to keep track of the trajectories of all particles. So that's rather heavy description. If you're working with fields, then you just have a simpler description, but that might still be heavy. I'll go back to that in a moment. But it's, in principle, fewer degrees of freedom to deal with. And associated to that question of level of description is how do you implement this description in a working algorithm, and is it easy to parallelize if you want to deal with very large systems? Another issue is that of flexibility, because you want to deal not only with very simple systems, but you want to deal with complex flows. So for example, turbulent flows for simple fluids. And you may want also to deal with complex fluids, for example, mixtures or suspensions or fluids in porous media and so on. And if you have that type of complexity, you need to implement boundary conditions that may be complicated in principle. So you want something that is simple in practice in order to implement these boundary conditions. So that also something you need to think about when designing your simulation algorithm. And finally, I'm not going to discuss that too much, but you need to capture also the effect of thermal fluctuations. And depending on your level of description, these thermal fluctuations may be easy or difficult to incorporate. So now I'm going to go through a few examples of different types of simulations for hydrodynamics. And the most obvious thing you could think of is simply solving directly the Navier-Stokes equation using what is called computational fluid dynamics. And the idea is simply to solve numerically the Navier-Stokes equation on a grid. So you will discretize space and have grid points in space where you will compute and evolve the hydrodynamic field, so the density at grid point xi at a given time, the velocity at the same grid point at a given time, and the pressure or the stress tensor at the same grid point. And then you can discretize numerically the Navier-Stokes equation. So there are many different algorithms to solve this numerically that depend on how you discretize the derivative, the time derivative, how you discretize the gradients, and so on. But essentially what you end up with is something that allows you to transform the hydrodynamic fields on the grid at a given time to the values of the fields on the grid at a next time step. And there are many ways of doing so, and it involves a large community of applied mathematicians. I'm not going to discuss that in details, but you should know that it's used. One issue with that is how to implement easily the boundary conditions, but that's also something you can do, and you can also parallelize the algorithm so that essentially you can do many things with that type of approaches, but that may not be relevant when you're moving down to the small scale where you have hydrodynamic fluctuations in particular. So at the other extreme you have molecular simulations, and again I'm not going to focus on that today because you've had other lectures on molecular simulations, but the idea is that if you have a very large system and simulate it for a very long time, you can analyze the trajectories, compute the stress tensor for each time along your trajectory, and then from this stress tensor compute the autocorrelation function of the different components. And then you have the Green-Kubo relations that tells you that this integral of the time correlation function for the stress tensor is related to the viscosity. So it gives you a way to compute the viscosity from a molecular model using molecular simulations. And you can also use molecular simulations to determine what type of boundary conditions you should apply at the interface between a given fluid and a given solid. For example, computing the slip lengths, as was done in this paper. So what you have here is a slab of liquid water between two walls, and you shear this slab by moving the flat wall on the top part in one direction and in the bottom part in another direction. And even though the density profile here along the slit pore is rather inhomogeneous at the interface, you still end up with a velocity profile that is linear. And if you had a non-slip, so a stick boundary condition at the interface, the velocity of the fluid at the interface should be equal to that of the liquid of the solid wall. And you see that it's not the case. So here the velocity of the liquid at the interface is different from that of the wall, and the same thing on the other side. And if you extrapolate, so if you take the tangent here, the slope, and extrapolate inside the fluid at which distance, inside the solid, excuse me, at which distance it would be equal to that of the wall, then it gives you a measure of the slip length, because it's related to the ratio between the slope here and the velocity. And so if you have a linear profile here, extrapolate, that gives you the slip length. And then you can investigate how this slip length depends on the interactions on the molecular level between the fluid molecules and the wall. So let me now finish this first lecture by illustrating two mesoscopic simulation techniques. So this is the paper from which the telescoping down cartoon was extracted from. And this paper is interested in the simulation of colloidal suspension. So you want to describe explicitly the colloidal particles, but you want to have a very simple description for the solvent, but keeping track of all its effects on the suspended particles. And this illustrates that you have many different ways of doing so. So I'm not going to discuss the Low-Anderson method, but the second course will be about lattice-Boltzmann, so I'm going to skip that for a moment. And I'm going to tell you about two other mesoscopic simulation techniques, namely dissipative particle dynamics and stochastic rotation dynamics. So you have two cartoons here that can tell you already that they have a different way of representing the fluid and representing how momentum is transferred through the fluid. But all these techniques you can use to simulate colloidal suspension. So depending on what exactly you want to do, you may choose one or the other. And that depends on what type of systems and what regime you are looking at. So starting with dissipative particle dynamics, the idea is in fact very similar to molecular dynamics. So you have explicit particles, but these particles are not meant to represent molecules, but rather to be effective particles that model a group of molecules. So it's what in polymer physics you would call a blob. So this is an effective particle that interacts with other effective particles, and typically to simulate a molecular fluid, it would be of the order of a few to 10 molecules represented by this effective particle or blob. And as you can imagine, if you want to look at the effective interactions between these blobs, they will look differently from what the interactions between two molecules look like. And in particular, you don't have a hardcore repulsion at short range, because the effective potential between these two blobs will be much softer. So the first type of interaction you have between blobs is simply the one due to conservative forces, but there will not be a derivative of a potential energy, but rather of a free energy, where you have averaged out some degrees of freedom. So that would be this Fc for conservative forces. And typically, you will have a finite energy to bring the center of mass of these two blobs at a given position. So it can be a large but finite energy. And it's a much softer repulsion between the blobs. Now, you want to also incorporate the other effects I've mentioned when discussing the effect of the solvent as a whole. And you will have pairwise dissipative forces that correspond to the friction between these blobs. So you have a conservative part that comes directly from the interaction, but you also have some dissipation due to the friction between the blobs, and it has to do not with the relative position of the blobs, but also to the relative velocities. And finally, associated with these dissipative forces, you also have a random force that is also pairwise additive, and that will re-inject the energy that is lost due to the dissipative part. So essentially what you're doing with this type of dissipative particle dynamics simulation is just like a molecular dynamics, but with a force that has an effective conservative part, a dissipative part that depends on the relative velocities, and a random force that will give rise to thermal motion. But at each time step, you have the position and velocities of your particles and compute these forces and then propagate the positions and velocities just as you would in a molecular dynamics simulation. And by doing so, you can simulate systems that are much larger than the one you would simulate with molecular dynamics. And for example, this is an illustration, a recent illustration of a fluid here in red, confined between walls. So you have wall atoms in blue, and the walls are coated with polyethylene glycol brushes, so short polymer chains in yellow. And what you can do then is look at the friction of this slab when you shear the system. So again, you're moving the walls in one direction on the top part and the other direction in the bottom part. And you will look at the force exerted on the walls by the confined liquid here. And you can look at how the friction depends on, for example, the grafting density of your polymer brushes, or the length of the brushes, or the nature of the interaction between the fluid and the polymer. For example, is it a good solvent for the polymer brushes or for the polymer chains or not, and so on. So it gives you a way to deal with systems that are much more complex than what you would simulate with molecular simulations. The second type of hydrodynamics, mesoscopic hydrodynamic simulations I wanted to talk about is called stochastic rotation dynamics. So that's the simulation used to do the sedimenting colloidal suspension I've shown earlier. And the idea is very different. So now you don't really care about the motion of effective particles within your fluid. You just want a description that will transfer momentum through the fluid as it should. And you want that description to be as simple as possible. And one way to do this is to represent the solvent by particles that are not molecules but really effective particles that don't interact with each other. So if they don't interact with each other, they have a ballistic motion. So they always keep their velocity, and it's very easy to do a molecular dynamics simulation with no interaction. You simply move with the same velocity at any time. So you will have straight lines for the motion of the fluid particle, but that will not, of course, give you the momentum transfer you need to describe hydrodynamic flows. The way this is done in stochastic rotation dynamics, or what is also called multi-particle collision dynamics, MPCD, is to add an additional ingredient to the dynamics of your fluid particles, namely after a given number of time steps, and you do this repeatedly, you divide your simulation box into cells. So the cells are represented here by the lines. And in each cell, you will do something a bit strange to your particles. You will look at the velocity of all your particles relative to the velocity of the center of mass in your cell. And then you will choose a random axis and rotate all these velocities relative to the velocity of the center of mass by a fixed angle. So the angle is fixed. It's the same for all the cells in your system, but you choose a different axis for each cell. And you do this rotation. So here you see that I've turned all vectors here anti-clockwise by a same angle around an axis perpendicular to the screen. And by doing so, you can show that you recover the Navier-Stokes behavior if you look at sufficiently long time scale and large time scales. And I'm not going to tell you about why this works, but the idea is that you can tune the viscosity and the mass density of your fluid by tuning or choosing your simulation parameters that are the number density of your particles to represent the fluid. You can choose the frequency at which you do the collision step, the size of the cells, the angle, and so on. And that gives you some flexibility to simulate any fluid and any flow you would like to simulate. And in particular, this one is rather popular for the simulation of colloidal suspension because it includes naturally thermal fluctuations. Finally, an illustration of the stochastic rotation dynamics technique. So this is a simulation of vesicle, so a soft membrane, if you want, flowing through a capillary. So the capillary is rather flat, so this is why it looks like a bean if you look on the sides, and it's rather wide, so the vesicle is rather deformed simply by confinement, but it's also deformed by the flow. As you can see here, it has a shape that is clearly modified by the flow, and that's the type of simulation you could use, for example, if you want to simulate blood vessels. Okay, so that's all I wanted to say for this first lecture. So if you have any questions, I'd be happy to take them, and then we can, I think, go for the coffee break and group photo. Any questions? Yes?
Your simulations, do you know if someone tried to consider the problem of protein foldings? Because if you take an amino acid, it should be about the size of one pure blood.
So that's a very good question. So there are groups looking at protein folding with coarse-grained models. Most of them use molecular simulations because they think that molecular details will matter, in particular the hydration of the protein on a very local scale that is not well captured by this type of mesoscopic models. But from your molecular simulations that are very long, you can make coarse-grained models that are probably realistic. I'm not aware of simulations where hydrodynamic effects would be included in these coarse-grained models. The one I have in mind are, for example, lattice models that are simpler in a sense that the one I'm going to describe with lattice Boltzmann, because they do not capture the effect of hydrodynamic flows. But it's true that typically protein folding may be influenced by flows in addition to molecular effects like hydration of sites on the molecular scale. Any other question? Everybody wants coffee, so if you have questions, I can answer later today. Thanks.